Hi, my name is Francisco Lozada, and this is an introduction to CircGR, which is a real-time multi-touch gesture recognition using circular measurements. I would also like to note that there were previous major contributions made by Ruben Balcazar and Francisco Ortega in the previous iteration of the project. So what is CircGR? CircGR is a non-symbolic multi-touch gesture template-based matcher. It uses circular measurements to represent gestures, requires as little as one example per template, supports user-defined gestures, and has early detection by classifying whether gestures are in progress. So why create CircGR? Well, multi-touch is not a solved problem, like many people would believe. Robust multi-touch gesture recognition increases as touch-enabled devices proliferate, making multi-touch gestures a prominent component of the user experience. Main reason why circular measures are used in CircGR is to improve classification performance. Circular statistics is primarily focused on data that represents time, direction, and orientation. These measures have no particular sense of magnitude, therefore they can be represented by unit vectors. A series of such vectors in two-dimensional space lie on the surface of a unit circle and are thus circular data. Template matching algorithms typically pre-process input to maximize classification performance. Pre-processing can include resampling, scaling, rotation, and translations of input, as well as additional technique-specific transformations. Circular measures are just a series of angles along with their descriptive statistics, in other words, mean, resultant vector, etc. A series of angles can be used to represent any given geometric curve by segmenting the curve into equal length vectors. Therefore, gesture representation in CircGR consists of two sets of n angles. One being spatial angles derived from a point's x and y input position, and temporal angles derived from a point's timestamp, or in other words, the time at which the touch input was created. Gesture resampling allows input gestures to have the same amounts of points as their template counterparts, simplifying template comparison. Therefore, resampling generates fixed number of interpolated points for each trace. Spatial angle alpha s is calculated from points pi and pi minus 1, as seen in the equation below. Note, traces with very little or no movements are treated as anchors and don't contribute angles. Temporal angle lambda t calculation immediately follows lambda s, or spatial angle calculation during resampling. Thus, there is an angle in t for every angle in s. The total duration of the gesture, delta g, starting at time ts, is wrapped around a circular interval. A temporal angle lambda t is calculated from the timestamp of interpolated point pi, as seen in the equation below. Each angle, spatial or temporal, is assigned three labels: a propagation label, a centripetal label, and a clock label. Temporal angles lambda t inherit all the labels assigned to spatial angles lambda s. Propagation labels consist of 8 directions that are based on the cardinal and intercardinal directions as shown in the figure. A buffer called the directional margin is defined around each axis direction. The centripetal labels consist of 2 directions, I for in and O for out, and are assigned relative Euclidean distances to the gesture's center point. Given 2 points, pi and pi minus 1 that generated lambda s, either I or O is assigned to lambda s, or the spatial angle, based on the conditions shown below. The last of the 3 labels is clock direction, determined from alpha I relative to alpha I minus 1. So tracing smallest arc between the subsequent observations yields either counterclockwise or clockwise. The overall classification flow is as follows. First, the 2D traces which are inputted are resampled. Then angles are generated and labeled, and then classification via template comparison is performed. For the classification in CircGR, input gestures are classified as a template with the smallest total distance, which in other words is the sum of all circular distances between angles of the template and of the input. Spatial angles are sorted, compared along similar labels, and unpaired observations are compared to gesture resultant angles. Temporal angles are compared in order generated across similar labels. Unpaired observations are penalized with a distance of pi. For the time complexity over endpoints, the gesture construction for input gesture has a worst case time complexity of n. Therefore, it's linear. For the classification, it is in worst case n log n, and therefore overall in worst case time complexity, all templates are compared resulting in t multiplied by n log n, where t is the number of templates. Finally, the contributions made this iteration were translating CircGR API from C# to C++ in order to provide a more cross-platform solution for gesture developers. I also implemented a scratchpad to demonstrate the API usage, and I wrote a custom gesture parser using a library called TinyXML to deserialize and serialize template and candidate gestures that were previously stored as GDML XML.
Hello, I would like to introduce you to the Leap Trainer and its companion device, the Leap Motion Controller. The Leap Motion Controller is a commercialized, palm-sized infrared sensor designed to make capturing hand and finger movements in 3D space affordable. Applying machine learning methods, this project hopes to extend the usefulness to, or revalidate the use of, the Leap Motion Controller's device for single-frame gesture recording and recognition. As the backbone of American deaf culture, gesture recognition on American Sign Language could potentially become an educational tool for children and adults. Alas, the Leap Trainer was built, a single-frame gesture recording and recognition system utilizing the compact and affordable Leap Motion Controller. The English alphabet in American Sign Language is a set of gestures recorded and recognition tested on. Applying k-nearest neighbor on recorded and trained frame vector data, experimental results obtained in this study show an average recognition rate of approximately 78% versus a test trained sample of 300 recorded frames per letter, with accuracy increasing as the set of trained recorded frames grows. Thank you for watching.
Hi there, my name is Hamilton Chavez. I am part of the ARVRVE for Computer Science Education project, version 1.0. The objective for this project is to increase the retention rate of computer science students in first-year courses. ARCSEducation has the objective of creating a set of learning activities to increase mastery of computer science topics through augmented reality. The platform used for developing is Unity, along with the Vuforia API for augmented reality. Vuforia has a feature called Virtual Buttons that lets you define an area on its marker-based system as an interaction domain. Users are able to touch that area in order to trigger events in Unity applications. The project includes a scene where students practice converting binary values to decimal or hexadecimal on their own personal preference. They use touch to trigger the virtual buttons in order to select their answer and see if they got it correct or wrong. Another scene serves as a set of reference models for the future use of creating a set of cards, where each card is a target for a different model to be displayed. These cards will serve as a set of reference cards that people can look back and remember various referential data.
CodeVR is an application designed to enhance computer programming concepts to computer science students. CodeVR achieves that by porting computer code to virtual reality, allowing users to interact with three-dimensional blocks. Such blocks contain code information and attributes that can be modified, added, or deleted. Once the user is satisfied, the blocks will be translated back into computer code. The current build supports Python, and it allows users to select valid Python code that gets drawn in virtual reality. Next iterations should focus on rendering more data from the code and saving changes to the Python file. Here's a quick demo of the current build.